In this video, we are going to combine in one circuit the step-down and the step-up topologies. This type of device is called the buck-boost converter. Firstly, we learned how to decrease the voltage coming from the PV side until you get to a boundary voltage of 0. Secondly, we learned how to increase the PV input voltage theoretically up to infinite. Now we will see the topology of the buck-boost converter that allows to step up and down the PV input voltage with one single circuit. Furthermore, we will compare the three devices and establish their efficiencies. Here is depicted the simplified schematic of a buck-boost converter. The components are the inductors, the flyback diode, the capacitor, and the resistive load. The topology is very similar to the buck converter, but now the coil and the flyback diode are inverted. The other important thing which is different is that now the polarity of the voltage across the load is inverted with respect to the input voltage. During the on cycle, the flyback diode basically separates the circuit in two sub-meshes. On the left-hand side sub-mesh, the coil is connected in series with the power generator, while on the right-hand side sub-mesh, we have the load in series with the capacitor, allowing the current to circulate in a loop. By balancing the voltages, we get that the voltage across the inductor is equal to the input voltage. We can thus compute the current variation during the on period, and notice that it increases when the switch is closed, since it is directly proportional to the input voltage. On the other hand, when the switch is off, it disconnects the input source, and then the magnetic field of the inductor becomes the driving force that drives the current through the load. As a consequence, the voltage across the inductor becomes the additive inverse of the output voltage. Remind that this is true only if we consider negligible the voltage across the flyback diode. Therefore, the current through the coil during the off period decreases because it is directly proportional to the additive inverse of the output voltage. After a certain amount of cycles, the buck-boost converter reaches a steady state of operation, and in continuous mode, the net variation in the inductor current after one entire switching cycle is 0. Therefore, we can work out this equation that relates the current variation during on mode and off mode by means of the two integrals previously calculated. The result is a relation that binds the output voltage and the input voltage as a function of the duty cycle. In the diagram, the output voltage is plotted as function of the duty cycle. Given a certain input voltage, we find that for D lower than 0.5, the device works as a buck converter, decreasing the incoming voltage. Instead, for D higher than 0.5, the voltage at the output side goes up, and theoretically it has no limit, tending to infinite. The very important thing to remember here is that now the sign of the voltage is inverse with respect to that of the input voltage. Now, just to wrap up the main concepts of the three topologies seen, we will compare them firstly according to the output voltage and then according to the input voltage. When we consider the output voltage as a function of the input voltage, we have that in case of buck converter for D equal to 0, also the output voltage is 0. And for D equal to 1, the maximum voltage achievable is the input voltage. So you can go anywhere between 0 and Vin. In a boost converter, the minimum output voltage is achieved when D is 0 and DT is equal to Vin, while when D is 1, Vout tends to infinite. Finally, a buck-boost converter can cover the whole range from 0 to infinite. Of course, if we work out the inverse relation between the input and output voltages, then we can find the input voltage as a function of the load voltage. So, for example, the buck converter requires an input voltage higher than the output one. The boost converter, as opposite, requires an input voltage that is lower than the output, so ranging from 0 to the output voltage. Lastly, the buck-boost converter once again covers the whole range from 0 to infinite. These are the three topologies that are generally used for accomplishing a DC-DC conversion. To calculate the efficiency of the converter, let's first define where the losses occur in the circuit. The efficiency of the converter is defined as the power output divided by the power output plus the dissipated power. This dissipated power has three sources. We have the losses in the switch, which depend on the type of switch. the switching speed and the resistance or the voltage drop across the switch. Then the PL is related to the fact that the switches are working at high frequencies, so there is also a loss inside the coil that is given by the resistance of the coil times the RMS value of the current flowing through it to the second power. This is a tweaked version of the Joule losses within the metallic spire of the coil. Finally, we also have resistive losses in the circuitry, and these are included under losses. For example, Joule losses in the copper lines on the board, or also losses in the other components. As you can see, there is no term that accounts for the capacitor or the flyback diode, and that's because we are assuming both of them lossless. Of course, capacitors and diodes are not exactly lossless. However, they have been neglected in this context for the sake of simplicity. Now, before the conclusion, I want to show you an example of a synchronous buck-boost converter, moving away from the ideal converter and closer to a more realistic topology. You see now that both the switch and the flyback diode are represented with a MOSFET, which is a transistor that we have already introduced. Notice that a MOSFET can work also as a flyback diode depending on how you control it. This choice of using a transistor instead of a diode is a choice made at production level. The reason is to reduce the losses in the diode and to lower the production steps by just using the same device and a set of controller to make the transistor work either as a switch or a diode. The controller is nothing else than the maximum power point tracking algorithm, so it is usually a circuitry customized with a hard-coded algorithm or maybe a programmable algorithm that controls these two parts of the converter. To conclude, the DC-DC converter section, we went through the motivation, definition, and the components inside the DC-DC converter. Then we look at three different topologies that culminate with the buck-boost converter. In this video, we gave you the definition of efficiency of the converter and found out where the losses are. In the next video, we will introduce the DC to AC solar inverter.